Chapter 3. Knowledge is Power. It is important not to underestimate the damage inflicted on AI during the mid-1970s. Many academics started to treat AI as a pseudoscience. The field has really only recently recovered from the reputational damage it suffered during the AI winter. But even as the Lighthill report was being circulated and its consequences were being felt, a new approach to AI was beginning to gain attention, which promised to overcome the problems that had led to AI getting such bad press. The problem with previous efforts, according to a new generation of researchers that burst onto the scene in the late 1970s and early 1980s, was that AI had focused too much on general approaches like search and problem-solving. These weak methods, it was argued, were missing a key ingredient that must surely be a crucial part of any intelligent activity: knowledge. The proponents of knowledge-based AI were convinced that capturing and using human knowledge was the key to progress in AI. A new class of knowledge-based AI systems began to emerge. These so-called expert systems used human expert knowledge to solve specific, narrowly defined problems. Expert systems provided evidence that AI systems could outperform humans in certain tasks, and, perhaps more important, for the first time, they showed that AI could be applied to problems of commercial interest. AI suddenly showed the potential to make money. And it was possible to teach the techniques of knowledge-based AI to a wide audience. A generation of graduates emerged determined to apply their practical AI skills. Expert systems made no claim to be general AI. Rather, the aim was to build systems that could solve very narrow, very specific problems that required considerable human expertise. Typically, these were problems in which a human expert had acquired expertise over a long period of time and where that human expertise was scarce. For the next decade, knowledge-based expert systems were the main focus of AI research. Enormous investment from industry flowed into the field. By the early 1980s, the AI winter was over. Another, much bigger AI boom was underway. In this chapter, we'll look at the expert systems boom, which lasted from the late 1970s to the late 1980s. We'll start by seeing how human expert knowledge can be captured and given to computers. And I'll tell you the story of Mycin, one of the most celebrated expert systems of the period. We'll see how researchers looked to try to build richer ways of capturing knowledge, using the power and precision of mathematical logic, and how this goal ultimately foundered. We'll then hear the story of one of the most ambitious and notorious failed projects in AI history, the Psych project, which tried to use human expert knowledge to solve the biggest problem of them all: general AI. Capturing human knowledge using rules. The idea of using knowledge in AI systems was arguably not a new one. Heuristics, as we heard in the previous chapter, were widely used in the Golden Age as a means to focus problem-solving in promising directions. Such heuristics can be understood as embodying knowledge about a problem. But heuristics only capture knowledge implicitly. Knowledge-based AI was based on an important new idea, that human knowledge about a problem should be explicitly captured and represented within an AI system. The most common scheme adopted for what came to be called knowledge representation was based on rules. A rule in the context of AI captures a discrete chunk of knowledge in the form of an if-then expression. Rules are actually rather simple, and best explained by way of an example. So, following are some rules written in English which are part of the folklore of AI. They capture knowledge for an expert system that assists a user in the task of classifying animals. If animal gives milk, then animal is mammal. If animal has feathers, then animal is bird. If animal can fly, and animal lays eggs, then animal is bird. If animal eats meat, then animal is carnivore. The way we interpret such rules is as follows. Each rule has an antecedent, the part after the if, and a consequent, the part after the then. For example, in the following rule, if animal can fly and animal lays eggs, then animal is bird, the antecedent is animal can fly and animal lays eggs, while the consequent is animal is bird. The usual interpretation of such a rule is that if the information that we currently have correctly matches the antecedent, then the rule fires, meaning that we may then conclude the consequent. For this rule to fire, we would therefore require two pieces of information: that the animal we are trying to classify can fly, and the animal we are trying to classify lays eggs. If we do indeed have this information, then the rule fires, and we conclude that the animal is a bird. This conclusion gives us more information, which can then be used in subsequent rules to obtain more information, and so on. Usually, expert systems interacted with a user in the form of a consultation. The user would be responsible for providing information to the system and answering questions posed by the system. Mycin, a classic expert system. Of the first generation of expert systems that emerged in the 1970s, perhaps the most iconic was mycin. The name derives from the fact that many antibiotics have mycin as a suffix. Mycin demonstrated for the first time that AI systems could outperform human experts in important problems, and provided the template for countless systems that followed. Mycin was intended to be a doctor's assistant, providing expert advice about blood diseases in humans. The system was developed by a team of researchers at Stanford University, including experts from Stanford's AI labs, led by Bruce Buchanan, and experts from Stanford's medical school, led by Ted Shortliff. The fact that the project benefited directly from the commitment of the people who actually knew the stuff the expert system was supposed to be expert in was a key factor in the success of mycin. Many later expert system projects failed because they lacked the necessary buy-in from the relevant human experts. Mycin's knowledge about blood diseases was represented using a slightly richer form of rules than we used in the animals example previously. A typical mycin rule, expressed in English, is as follows. If 1. The organism does not stain using the Gram method, and 2. The morphology of the organism is rod, and 3. The organism is anaerobic, then there is evidence, 0.6, that the organism is Bacteroides. Mycin's knowledge about blood disease was encoded and refined over a period of about 5 years. In its final version, the knowledge base contained hundreds of rules like this. Mycin became iconic because it embodied all the key features that came to be regarded as essential for expert systems. First, the operation of the system was intended to resemble a consultation with a human user, a sequence of questions to the user, to which the user provides responses. This became the standard model for expert systems, and mycin's main role, diagnosis, became a standard task for expert systems. Second, mycin was able to explain its reasoning. This issue, the transparency of reasoning, became crucially important for the applications of AI. If an AI system is operating on a problem that has significant consequences, in the case of mycin, potentially life or death consequences, then it is essential that those who are asked to follow the system's recommendations have confidence in them, and for this, the ability to explain and justify a recommendation is essential. Experience shows that systems operating as black boxes, making recommendations without the ability to justify them, are treated with great suspicion by users. Crucially, mycin was able to answer questions relating to why it had reached a particular conclusion. It did this by producing the chain of reasoning that led to the conclusion. The rules that were fired and the information that had been obtained leading to these rules being fired. In practice, the explanation capabilities of most expert systems ultimately boiled down to something similar. While not ideal, such explanations are easy to produce, and give at least some mechanism through which to understand the system's conclusions. Finally, Mycin was able to cope with uncertainty. Situations in which the information provided was not known to be true with certainty. Handling uncertainty turned out to be a ubiquitous requirement for expert system applications and AI systems more generally. In systems like Mycin, it is rarely the case that a definite conclusion can be drawn on the basis of a particular piece of evidence. For example, when a user has a blood test that comes back positive, then that provides some useful evidence that can be taken into consideration by the system. But there will always be the possibility of a faulty test, a false positive or false negative. Alternatively, if a patient displays some symptom, then this may be indicative of a particular ailment, but not enough to conclude with certainty that the patient suffers from the ailment. To be able to make good judgments, expert systems need to be able to take such evidence into account in a principled way. In trials carried out in 1979, Mycin's performance in diagnosing blood diseases was shown to be at a comparable level to human experts when evaluated on 10 real cases and above the level of general practitioners. This was one of the first times that an AI system demonstrated capabilities at or above human expert level in a task of real significance. Boom times again. Mycin was just one of a number of high-profile expert systems that appeared in the 1970s. The Dendral project, also from Stanford University, was led by Ed Feigenbaum, who became one of the best-known advocates of knowledge-based systems and is often regarded as the father of expert systems. Dendral aimed to help chemists determine the chemical structure of a compound from the information provided by mass spectrometers. By the mid-1980s, Dendral was being used by hundreds of people every day. The R1XCon system was developed by Digital Equipment Corporation, DEC, in order to help configure their popular VAX computers. By the end of the 1980s, the system had about 17,500 rules, and the developers claimed it had saved the company about $40 million. Dendral showed that expert systems could be useful. Mycin showed they could outperform human experts at their own game, and R1XCon showed that they could make serious money. These success stories attracted a lot of interest. AI, it seemed, was ready for business. Massive investment flowed in. A flurry of startup companies rushed to cash in on the boom. Companies across the world scrambled to get in on the expert systems boom, and not just software companies. By the 1980s, industry was beginning to understand that knowledge and expertise were important assets that could be nurtured and developed to profitable advantage. Expert systems seemed to make this intangible asset tangible. The concept of a knowledge-based system resonated with the then prevailing view that Western economies were entering a post-industrial period, in which new opportunities for economic development would come primarily from the so-called knowledge-based industries and services rather than from manufacturing and other traditional industries. A grand new job title emerged: Knowledge Engineer. Logical AI. Although rules became established as the de facto knowledge representation scheme for expert systems, the issue of knowledge representation troubled AI researchers. One problem was that rules were just too simple to capture knowledge about complex environments. Rules of the type used in Mycin were not well suited to capturing knowledge about environments that change over time, or that contain multiple actors, human or AI, or where there is uncertainty about the actual state of the environment. Another problem was that researchers wanted to understand what the knowledge in their expert systems actually meant, and to be sure that the reasoning that the system undertook was robust. In short, they wanted to provide a proper mathematical basis for knowledge-based systems. The solution that began to emerge in the late 1970s was to use logic as a unifying scheme for knowledge representation. To understand the role that logic played in knowledge-based systems, it helps to know a little about what logic is and why it was developed. Logic was developed in order to understand reasoning, and in particular, what distinguishes good, sound reasoning from bad, unsound reasoning. Let's see some examples of reasoning, both sound and unsound. All humans are mortal. Emma is human. Therefore, Emma is mortal. This example illustrates a particular pattern of logical reasoning called a syllogism. And I hope you will agree that the reasoning here is perfectly reasonable. If all humans are mortal and Emma is human, then Emma is indeed mortal. Now consider the following example. All professors are good-looking. Michael is a professor. Therefore, Michael is good-looking. You may be less comfortable with this example, because while you were happy to accept the statement all humans are mortal, you would probably balk at the statement all professors are good-looking. It obviously isn't true. However, from a logical point of view, there is nothing at all wrong with the reasoning in this example. It is perfectly sound. If it were indeed the case that all professors are good-looking, and it was also the case that Michael is a professor, then it would be entirely reasonable to conclude that Michael was good-looking. Logic is not concerned with whether the statements you start from, the premises, are actually true or not, simply whether the pattern of reasoning you use and the conclusions you draw would be reasonable if the premises were indeed true. The next example, however, shows some unsound reasoning. All students are hard-working. Sophie is a student. Therefore, Sophie is rich. The pattern of reasoning here is not sound, because it is not reasonable to draw the conclusion that Sophie is rich given the two premises. Sophie may be rich, but that isn't the point, which is that you can't reasonably derive this conclusion from the two given premises. So, logic is all about patterns of reasoning, of which syllogisms, as shown in the first two examples, are perhaps the simplest useful examples. Logic tells us when we can safely draw conclusions from premises, and the process through which this is done is called deduction. Syllogisms were introduced by the ancient Greek philosopher Aristotle, and for more than a millennium they provided the main framework for logical analysis. However, they capture a very limited form of logical reasoning, completely inappropriate for many forms of argument. From early on, mathematicians have had a strong interest in trying to understand the general principles of sound reasoning, as mathematics is ultimately all about reasoning. The job of a mathematician is to derive new mathematical knowledge from existing knowledge, making deductions, in other words. By the 19th century, mathematicians were troubled about the principles of what they were doing. What does it mean, they wondered, for something to be true? How can we be sure that a mathematical proof represents a reasonable deduction? How can we even be sure even that 1 + 1 = 2? From about the mid-19th century, mathematicians started to investigate these questions in earnest. In Germany, Gottlob Frege developed a general logical calculus within which we can for the first time start to see something resembling the full framework of modern mathematical logic. Augustus de Morgan in London and George Boole in Cork, Ireland, started to show how the same kinds of techniques that are used for problems of algebra can be applied to logical reasoning. In 1854, Boole published some of his findings under the gloriously immodest title of The Laws of Thought. By the start of the 20th century, the basic framework of modern logic had been largely established, and a logical system had emerged that to the present day provides the language that underpins almost all work in mathematics. The system goes by the name of first-order logic. First-order logic is the lingua franca of mathematics and reasoning. Within this one framework, we can capture all the types of reasoning studied by Aristotle, Frege, De Morgan, Boole, and others. And in just the same way, within AI, first-order logic seemed to offer a rich general framework for capturing human knowledge. The paradigm of logic-based AI was thus born. and one of its earliest and most influential advocates was John McCarthy. McCarthy described his vision for logical AI as follows. The idea is that an agent can represent knowledge of its world, its goals, and the current situation by sentences in logic and decide what to do by deducing that a certain action or course of action is appropriate to achieve its goals. The agent here is the AI system. The sentences in logic that McCarthy refers to are precisely the statements like all humans are mortal and all professors are good-looking that we saw previously. First-order logic provides a rich, mathematically precise language with which such statements may be expressed. A rather stylized illustration of McCarthy's vision for logical AI is shown in Figure 5 on the accompanying document. We see a robot operating in a blocks world type of environment. The robot is equipped with a robot arm and with a perception system that is used to obtain information about its environment. Within the robot, we see a logical description of the environment with statements like on brackets A, table, close brackets, on brackets C, A, close brackets, and so on. These statements are in fact expressions of first-order logic, and for the scenario shown in Figure 5, it is pretty obvious what they are intended to mean. On brackets X, Y, close brackets, means that the object X is on top of object Y. Clear brackets X, close brackets, means that there is nothing on top of object X. And empty brackets X, close brackets, means that X is empty. The role of the internal logical representation for the robot is to capture all the information that the agent has about its environment. It became common to refer to this representation as the beliefs of the system. The fact that the robot's belief system contains the expression on brackets A, table, close brackets is then taken to mean that the robot believes that block A is on the table. We need to be careful with such terminology, though. While it is helpful to use a vocabulary that we are familiar with when we populate the robot's belief system, on brackets X, Y, close brackets is pretty self-explanatory for human readers, the meaning of an expression such as this, when present in the robot's belief base, is ultimately derived from the role it plays in the behavior of the robot. It only really counts as a belief if, when the robot has this in its knowledge base, the robot acts as if it believes that X is on top of Y. The task of the perception system in Figure 5 is to translate the raw information provided by the robot's sensors into the internal logical form used by the robot. As we have already mentioned, this is by no means a trivial thing to do, a point to which we will return later. Finally, the actual behavior of the robot is defined through the robot's logical deduction system, its inference engine. The core idea in logical AI is that the robot reasons logically about what it should do. It deduces what it should do next. Overall, we can envisage the robot continually operating on a cycle of observing its environment through its sensors, updating its beliefs about its environment, deducing what the next action to perform should be, performing this action, and then starting the whole process again. It is important to understand why logic-based AI was so influential. Perhaps the most important reason is that it makes everything so pure. The whole problem of building an intelligent system is reduced to one of constructing a logical description of what the robot should do. And such a system is transparent. To understand why it did something, we can just look at its beliefs and its reasoning. There are, I think, other, less obvious reasons why the logical approach was so influential. For one thing, it is appealing to imagine that reasoning provides the basis for the decisions that we make. And when we reason, we seem to do so in sentences. When contemplating the merits of various courses of action, we might have a mental conversation with ourselves, discussing the pros and cons of each. Logic-based AI seems to reflect this idea. Psych, the ultimate expert system. The so-called Psych project was arguably the most famous experiment in the period of knowledge-based AI. Psych was the brainchild of Doug Lenat, a gifted AI researcher who combined outstanding scientific ability with unwavering intellectual conviction and a decided ability to persuade others to buy into his vision. Lenat rose to prominence in the 1970s with a series of impressive AI systems which in 1977 earned him the Computers and Thought Award, the most prestigious award that can be given to a young AI scientist. In the early 1980s, Lenat became convinced that the knowledge is power doctrine had applications far beyond the construction of narrowly focused expert systems. He was convinced it provided the key to general AI, the grand dream. Here is what he wrote with co-author Ramanathan Guha in 1990. We don't believe there is any shortcut to being intelligent, any yet-to-be-discovered Maxwell's equations of thought. No powerful formalism can obviate the need for a lot of knowledge. By knowledge, we don't just mean dry almanac-like or highly domain-specific facts. Rather, most of what we need to know to get by in the real world is too much common sense to be included in reference books. For example, animals live for a single solid interval of time. Nothing can be in two places at once. Animals don't like pain. Perhaps the hardest truth to face, one that AI has been trying to wriggle out of for 34 years, is that there is probably no elegant, effortless way to obtain this immense knowledge base. Rather, the bulk of the effort must, at least initially, be manual entry of assertion after assertion. And so, in the mid-1980s, Lenat and colleagues set themselves the task of creating this immense knowledge base, and the Psych project was born. The ambition in the Psych project was mind-boggling. To operate as Lenat envisaged, Psych's knowledge base would need a complete description of consensus reality, the world as we understand it. Pause for a moment to reflect on this challenge. Somebody would have to explicitly tell Psych that, for example, an object dropped on planet Earth will fall to the ground, and that it will stop moving when it hits the ground, but that an object dropped in space will not fall. A plane that runs out of fuel will crash. People tend to die in plane crashes. It is dangerous to eat mushrooms you don't recognize. Red taps usually produce hot water, while blue taps usually produce cold water. And so on. All the everyday knowledge that a reasonably educated person unwittingly carries with them would need to be explicitly written down in Psych's own special language and fed to the system. Lenat estimated the project would require 200 person-years of effort, and the bulk of this was expected to be in the manual entry of knowledge, telling Psych all about our world and our understanding of it. Lenat was optimistic that before too long, Psych would be able to educate itself. A system capable of educating itself in the way Lenat envisaged would imply that general AI was effectively solved. Thus, the Psych hypothesis was that the problem of general AI was primarily one of knowledge, and that it could be solved by a suitable knowledge-based system. The Psych hypothesis was a bet, a high-stakes bet, but one that, if it proved successful, would have world-changing consequences. One of the paradoxes of research funding is that sometimes it is the absurdly ambitious ideas that win out. Indeed, some research funding agencies go out of their way to encourage world-vaulting ambition over safe but plodding proposals. Perhaps this was the case with Psych. In any case, in 1984, Psych received funding from the Microelectronics and Computer Technology Corporation, MCC, in Austin, Texas, and the project was launched. Of course, it didn't work. The first problem was that nobody had ever tried to organize the whole knowledge of human consensus reality before. Where on earth do you begin? For a start, you need to agree all the vocabulary that you are going to use and how all the terms you use relate to one another. This problem, defining your basic terms and concepts and organizing your knowledge around them, goes by the grand name of ontological engineering. And the ontological engineering challenge posed by Psych was far greater than any other project that had been attempted previously. Lenat and colleagues rapidly discovered that their original ideas about how to structure the knowledge that Psych would use and the way in which this knowledge would be captured was simply too naive and imprecise, and some way into the project they found they had to start again. Despite these setbacks, a decade into the project, Lenat was still full of cheerful optimism, and in April 1994, his optimism caught the attention of Vaughan Pratt, a computer science professor at Stanford University. Pratt is one of computing's leading theoreticians, used to thinking about the fundamental nature of computing using the precise and pedantic language of mathematics. He was intrigued by a presentation on Psych and asked for a demo. Lenat agreed, and Pratt went to see a demo of Psych on April 15, 1994. In advance of the visit, Pratt wrote to Lenat to outline his expectations. He gave a list of the kinds of capabilities he was expecting to see, based on published scientific articles about Psych. "I'm assuming the demo will work best if my expectations are well matched to Psych's current capabilities," Pratt wrote. "If I arrive expecting too much, I may go away disappointed. But if my expectations are set too low, we may spend too long on things that don't do justice to Psych's full range of abilities." He did not receive a reply. The demonstration itself started with some straightforward illustrations of modest but genuine technical accomplishments that Psych was capable of, identifying some inconsistencies in a database that required some reasoning on behalf of Psych. So far, so good. Then, Lenat started to stretch Psych's capabilities a little. The second demonstration involved Psych retrieving images according to requirements that were written in ordinary English. The query, "someone relaxing," resulted in a picture of 3 men in beachwear holding surfboards. Psych had correctly made a link between surfboards, surfing, and relaxing. Pratt scribbled down the chain of reasoning that Psych took to get to this link. It required nearly 20 rules, involving some that seemed slightly strange to us. "All mammals are vertebrates" was one of the rules required to get there. The version of Psych that Pratt saw had 500,000 rules. Pratt then wanted to explore one of the most central features of Psych, its practical knowledge of our world. For example, Pratt asked whether Psych knew that bread was food. His host translated the query into the rule language used by Psych. "True," responded Psych. "Does Psych consider bread to be a drink?" asked Pratt. This time, Psych got stuck. Lenat tried telling it explicitly that bread is not a drink. It still didn't work. "After a bit of fiddling, we dropped this question," Pratt reported. They went on. Psych seemed to know that various activities caused death, but not that starvation was a cause of death. In fact, Psych didn't seem to know anything about starvation. Pratt went on to explore questions about planets, the sky, and cars, but it rapidly became clear that Psych's knowledge was sketchy and unpredictable. For example, it didn't know that the sky was blue or that cars typically had 4 wheels. Based on his expectations raised by Lenat's presentation, Pratt had prepared a list of more than 100 questions to ask Psych, which he hoped would start to explore the extent of Psych's common-sense understanding of our world. For example, if Tom is 3 inches taller than Dick, and Dick is 2 inches taller than Harry, how much taller is Tom than Harry? Can 2 siblings each be taller than the other? Which is wetter, land or sea? Can a car drive backward? Can a plane fly backward? How long can people go without air? These are all pretty basic questions to ask about our everyday world, but they could not be meaningfully asked of or answered by Psych. Reflecting on his experience, Pratt was careful with his critique of Psych. Perhaps Psych had made some progress toward the goal of general intelligence, he speculated. The problem was it was impossible to tell how far, because Psych's knowledge was so patchy and unevenly distributed. If we ignore the inflated expectations, then we can see that Psych taught us a lot about the development and organization of large knowledge-based systems. And, to be strictly accurate, the Psych hypothesis that general AI is essentially a problem of knowledge, which can be solved via a suitable knowledge-based system, has been neither proved nor disproved yet. The fact that Psych didn't deliver general AI doesn't demonstrate that the hypothesis was false, merely that this particular approach didn't work. It is conceivable that a different attempt to tackle general AI through knowledge-based approaches might deliver the goods. In some ways, Psych was just ahead of its time. 3 decades after the Psych project began, Google announced the Knowledge Graph, a large knowledge base which Google used to augment their search services. The Knowledge Graph has a vast array of facts about real-world entities, places, people, movies, books, events, which are used to enrich the search results that Google finds. When you type in a query to Google, it typically contains names and other terms that refer to real things in the world. For example, suppose you search Google with the query Madonna. A simple web search would respond with web pages that contain the word Madonna. But a search engine can be much more helpful if it understands that the character string Madonna refers to a popular singer, real name Madonna Louise Ciccone. So, if you search for Madonna on Google, you will find that the response for your query includes an array of information about the singer, which will answer most routine questions that people ask about her: date and place of birth, children, most popular recordings, and so on. One key difference between Psych and the Google Knowledge Graph is that knowledge in the Knowledge Graph is not hand-coded, but is automatically extracted from web pages such as Wikipedia. In 2017, it was claimed the system contained about 70 billion facts about 500 million entities. Of course, the Knowledge Graph does not aspire to general intelligence, and it isn't clear to what extent it involves actual reasoning of the kind that was so central to the knowledge-based system's view of the world. But nevertheless, I think there is some Psych DNA in the Knowledge Graph. However we might try to justify it retrospectively, the sad fact is that Psych's main role in AI history is as an extreme example of AI hype, which very publicly failed to live up to the grand predictions that were made for it. Cracks appear. Like so many versions of AI that are beautiful in theory, knowledge-based AI proved to be limited in practice. The approach struggled even with some reasoning tasks that seem absurdly trivial to us. Consider the task of common-sense reasoning, one classic example of which is given by the following scenario. You are told Tweety is a bird, so you conclude Tweety can fly. Later, though, you are told that Tweety is a penguin, so you retract your earlier conclusion. At first sight, it looks like this problem ought to be easy to capture in logic. It looks, in fact, very much like the syllogisms that we saw earlier should do the job. As long as our AI system had the knowledge, if X is a bird, then X can fly, then given the information that X is a bird, it should be able to deduce that X can fly. Well, so far so good. The difficulty comes with what happens next, when we are told that Tweety is a penguin. Then we need to retract, take back our earlier conclusion that Tweety can fly. But logic cannot cope with this. In logic, adding more information never eliminates any of the conclusions you obtained earlier. But that is precisely what is going on here. The additional information, Tweety is a penguin, causes us to eliminate our earlier conclusion, Tweety can fly. Another problem in common-sense reasoning arises when we encounter contradictions. Here is a standard example, called the Nixon diamond, from the literature. A standard pictorial representation of the scenario has a diamond shape. Quakers are pacifists. Republicans are not pacifists. Nixon is a Republican and a Quaker. Try to capture this scenario in logic, and a disaster ensues, because we end up concluding that Nixon both is and is not a pacifist, a contradiction. Logic fails utterly in the presence of such contradictions. It cannot cope, and it can tell us nothing useful at all. Yet, this is the kind of contradictory situation we all encounter every day of our lives. We are told that taxes are good, and we are told that taxes are bad. We are told that wine is good for us, and that wine is bad for us, and so on. It's ubiquitous. The problem, once again, is that we are trying to use logic for something it was not intended for. In mathematics, if you encounter a contradiction, then that means you made a mistake. These problems seem almost comically trivial, but they were major research challenges for knowledge-based AI in the late 1980s. They attracted some of the smartest people in the field, and they were never really solved. It also turned out to be harder to build and deploy successful expert systems than it first appeared. The main difficulty was what became known as the knowledge elicitation problem. Put simply, this is the problem of extracting knowledge from human experts and encoding it in the form of rules. Human experts often find it hard to articulate the expertise they have. The fact that they are good at something does not mean that they can tell you how they actually do it. And human experts, it transpired, were not necessarily all that eager to share their expertise. After all, if your company had a program that could do what you do, why would they keep you? Concerns about AI replacing people are nothing new. By the end of the 1980s, the expert systems boom was over. The technology of knowledge-based systems could not be said to have failed because many successful expert systems were built in this period, and many more have been built since. But once again, it seemed, the reality of what AI had actually produced had not lived up to the hype.